Hello everyone, this is your brief summary of differentiation. First principles, your rules, increasing, decreasing, max and min, point of inflection. And then we'll do the rates of change and integration tomorrow. But for today, we'll start off with first principles. Now, you will always know when to use first principles because they'll ask you. They will say, find the derivative of the following function by using first principles. So watch out for them asking you to do so. And if they ask you to do so, you need to know this formula, you need to use it. So the limit as h goes to 0 of the f of x plus h minus f of x all over h. That formula is not in the log tables and you need to know it. And just here's an example down here to the right. Some things students struggle with is finding if that is f of x, finding the f of x plus h. So wherever you have x, you replace it with x plus h. They've tended in the Leaving Cert in the past to ask quadratic functions. Sometimes they try to disguise quadratic functions by writing it like that. So I think it's probably easier just to multiply it out, have it as simple as possible going into first principles, and then apply the definition. As you apply the definition and multiply everything out, things will cancel, and what will happen, if you have a quadratic anyway, what will happen is that there'll be a h, you'll be able to factor out a h from the numerator. Because the goal is to let h be 0, but as long as there's a h in the denominator, you can't let h be 0. So that's the problem. But by the time you reach down here, down the fourth row down, if you factor out a h from the numerator, then the h's will cancel, and then you can let h be 0, and you get that the derivative is this. And with first principles, you can always check your answer pretty quickly by differentiating the normal way. You know, when you look at that quadratic function, 2x squared minus 13x minus 7, its derivative is 4x minus 13. Okay, so know your definition. When you apply the definition, do all the algebra you can to simplify matters. In particular, try to get rid of the h out of the denominator in a legitimate way, of course, ideally by factoring out a h in the numerator and cancelling them out. And then you can let h go to 0 and quickly check your answer. Okay, then the rules that you have on your log tables on page 25 are the product rule, and you need to know when you apply each of the following rules. So the product you apply when you have a product, one function times another function. Here's a few examples of instances where you'd use the product rule, one function times another function. All right. And then the quotient rule you use when you have one function divided by another function. So examples here where you might use the quotient rule are the following. And in each case there, with the product and quotient rule, let u be one of the functions, v be the other. With the quotient, you have to be a bit more careful because v must be the denominator. Whilst with product, it doesn't matter which one's which. And then you find du dx and you find dv dx, and then you put everything back together according to the rules in your log tables. And I didn't write them down here because they're in your log tables, page 25. So you use them there. Now, the trickiest one, the one they quite like to ask if they're asking an individual differentiation problem, is the chain rule. Watch out for the inner functions. So if you see a function, and on the inside, where there normally would be an x, like on page 25, you have the derivative of sine x, you have the derivative of e to the x, ln x, tan inverse of x. If where x usually is, if there's a more complicated function than x, then you need the chain rule, and you let u be the inner part. You write y in terms of u. You find du dx and dy du, so the derivative of each part with respect to the variable that it depends on. And then the chain rule says dy dx is dy du dx. When using the chain rule there, make sure that these two line up. So dy dx is equal to dy dx, and these du's are equal to each other. And then you put everything back together using that, and just make sure when you get back to dy du, instead of minus sine u, you have minus sine of what we let u equal, which was x squared plus 7x. Like finally the derivative should be completely in terms of x. Okay, so watch out for that, for the chain rule. So if you have a more complicated inner function, so not just x, but something more complicated on the inside, the minute you spot that, let u be that more complicated thing. And then, so you can use some of the log laws to help you simplify a function before you differentiate, okay? So if you look at this example over here, like that's a fairly convoluted function to have to differentiate, the ln of the square root of 5x over sine x. You see the quotient rule, you see chain rule, let's see two chain rules. But if you use your log laws, you could simplify and make life much easier when you go to differentiate. So for example, here, the square root is the power of a half. And then when we have a power, we can bring that in front to get a half ln of the quotient. But then ln of one function divided by another is the ln of the top minus the ln of the bottom. And then you can go a step further here, you're going to say that is 5 times x, which is the ln of 5 plus the ln of x. So it's a half times all of that minus a half times that. And when you distribute out the half in the first bracket there, you end up with a half ln of 5 plus a half ln of x minus a half ln of sine x. And half ln of 5, that could be misleading. Might look more complicated than it is. It's just a number, so the derivative is 0, it's a constant. A half ln of x, the derivative of ln x is 1 over x, so you have a half 1 over x. And then you'd need the chain rule for this one here, and it turns out to be that. So after using the log laws, life becomes much easier. Just watch out for that opportunity to use log laws to make the function much easier before you go and differentiate. Okay, so there's first principles and all your rules, product rule, quotient rule, chain rule. And now moving on to the applications of differentiation and the most important fact in all of calculus. Big statement right there. The most important fact in all of calculus is that the slope of the tangent line to a curve at a point is given by the derivative. So the minute you hear about a tangent line to a curve, think about taking the derivative to get the slope of that tangent line. Now, unless it's a tangent line to a circle, kind of 5% of the time they're talking about tangent lines to circles, if you're in a circle question, and then that's kind of a separate category, but 95% of the time where they're talking about tangent lines, they're talking about tangent lines to curves, and if you want the slope of the tangent line, it's given by the derivative at the particular point that you're at. Okay, here's an example. So f of x equals x squared. The derivative of f prime of x is 2x. The derivative at 1 is 2. So this slope here of this tangent line is 2. The derivative changes based on what point you're at. Like if we're at this point, green point back here, the derivative is going to be negative. And if we're at the point 0, 0, the derivative is going to be 0 because you have a horizontal tangent line. So the derivative is a function in its own right. It is 2x. It depends on what x value you're at, what the slope of the tangent line is. But coming back up here to the top left, increasing, the derivative can tell us something about the function. So if a function's increasing, then the tangent line has a positive slope, i.e. the derivative is greater than 0. Okay, so function increasing, you know the tangent line should have a positive slope, and we know that the slope of the tangent line is given by the derivative, so the derivative is positive. And then equally, when the function is decreasing, the derivative is going to be negative because the tangent line has a negative slope. To look for a max or a min, at a max or a min, look at the graph here. The tangent line is horizontal, okay? So at this little point here, -1, where we have a max, the derivative at -1 is 0. It's important to know that at a point where you have a max or a min, at a turning point like that, the derivative is 0, and hence when you plug the value of x into the derivative, you'll get 0. And that helps us to find a max or a min. So if you come over here to find a max or a min, you solve the derivative equal to 0. That's because you're looking for places where you might have a horizontal tangent line. Okay. Then the thing is, if you have the function and you don't see the graph, then you wouldn't know whether the value, at, for example, -1 down here or 2 over here, you wouldn't know whether you get a max or a min at those values. So how you figure that out in general is from point 2 here, you sub the values from 1 into the second derivative. And if the second derivative at a point is negative, then you have a max at that point, and if the second derivative is positive, you have a min at that point. And just be careful, big note here, at that point you'd have the x-coordinate of the max or the min, and to go back and find the actual coordinates at the point, you need to find the y-coordinates, but always and ever, if you're looking for the y-coordinates, you sub the x value back into the original function to get the y value, because at this point on your page you could have the function, the first derivative, the second derivative, so it could be very easy to sub the x value into the wrong function, so back into the original function. And then for a point of inflection, you solve the second derivative equal to 0. Now, all of these things in this page, increasing, decreasing, max, min, inflection point, all the consequences for the derivative you need to know, whether the derivative is positive, negative, 0, second derivative is 0, you need to know all of those. They're not in your log tables. And the most important fact up here, that the slope of the tangent line at a point is given by the derivative, you need to know that. And we'll talk about rates of change and acceleration tomorrow.